Hi guys, we're going to look at the first concept in data representation, which is converting between number bases. Now, why do we care about this? In the end, all a computer can really store is whether a switch is on or off. It might do that by storing an electron or not storing an electron. It might do that by, on a magnetic disk, it being pointing positive to negative or vice versa. But fundamentally, all your computer understands are on and offs. Now, we don't really care about on and off, otherwise known as 1 and 0 to make it simpler. You might see a symbol like this in your house, and you might see it on TV sets, maybe on your remote control. And if you look carefully, all it is simply a 0 and a 1. 0 signifying that it's off, and a 1 that's signifying that it's on. Now, we don't actually care about on and offs. In our world, what we care about are images and sound. We care about numbers and characters. So we have to find some way that we can use these ones and zeros to convert to all the things that we care about in our world. And that's what data representation is the big picture of it. It's about taking these ones and zeros and using them to show images and sound, etc. In today's lesson, we're going to look about how we represent Denary. Those are whole numbers, 1 to 10 or 0 to 9. Hexadecimal, that'll be a new concept, but it's converting between binary and hexadecimal, and finally between decimal or Denary into hexadecimal. Okay, so let's talk about how we're going to convert from binary, that's the ones and zeros, into Denary, and that's our number system, the one you grew up learning about. And let's first have a consideration of Denary. So I'm going to give a number here. I'm going to give 429. Now, something you'd have learnt about a long time ago is that actually these are different units. You'd say that the 9 is units of 1, so 9 units of 1. The 2 is units of 10. And finally, the 4 was units of hundreds. So you have 4 100s, 2 10s, and 9 1s. Now, I want to appreciate for a second, there's a relationship between each of these jumps that go across. When it goes from 1 to 10, 10 to 100, the next one will be thousands. That relationship is that each time it goes across, what happens is it is timesing it by 10. And that is why sometimes you'd even refer to the Denary system as the base 10 system. Now, all number systems actually obey some quite consistent laws. And if I said that binary is the base 2 system, well, we could think about that for a second. We could say that the first column is going to be 1. Now, if base 10 multiplied by 10 for each column going across in this direction, base 2 is going to multiply by 2 as we go across in this direction. So the first column is going to be lots of 1s. Then it'll be lots of 2s. It'll multiply by 2 again. So it'll be lots of 4s. Next time it will be 4 times 2, so it'll be 8, and onwards it would go. Now, unlike Denary, when I can go from 0 to 9, with binary I can only have 2 values, 0 representing off, and 1 representing on. So I can say 1, 0, 1, 1. That is a binary number. And the question is, how are we going to allow ourselves to convert that back to Denary? Well, you know what? It's actually really quite straightforward. All you do is every time there's a 1 in one of these columns, you add up the value at the top. So if there's a 1 here, it's an 8. 1 here, you add 4 to it. Since it's a 0, that means it's off. You ignore this one, and that's a 1 plus a 1 there. So actually, this number we can figure out quite straightforward. It's going to be 8 plus 4 plus 1. And we knock out we don't do the 2, like I say, because it's on 0. So 8 plus 4 is 12 plus 1. That's actually the number 13. A little bit more terminology. You call each of these things here, you call them digits. And again, that's because they relate to our digits, our fingers. Now, each of these going across here, these have a name as well. These are called bits. If you refer to this value here, you say it's a 3-digit number. This one, you say it's a 4-bit number. There's some other terminology we could learn as well. 4 bits like this is called a nibble. See, computer scientists have a sense of humor. If we have 8 of these, or so 8 bits, it would be a byte. Now, so far, we've shown how you can convert from a binary bit into digits, into a denary. We need to show it in reverse now, so we're going to do a quick calculation here. We're going to say, what is 192 in binary? Now, that's going to be a number that we're not going to be able to hold with just 4 bits like this. The biggest number we can make here is 8 plus 4 plus 2 plus 1. So that'd be the number 15. FYI, the smallest number is if we set all these to 0, so it would be 0. So a nibble goes from 0 to 15. To allow us to do 192, we're going to use 8 bits. And I hope you can remember what 8 bits were. 8 bits were known as a byte. So what we're going to do is we're going to do a byte's worth of, 8 bits worth. So we'll start, as we did before, with 1. The next thing we'll want to do is, because it's base 2, is multiply by 2. So it'll be 2. Then it's 4, 8, 16, 32, 64, and finally 128. And that, because there are 8 of them, are 8 bits. Again, as I say, a byte. So we want to convert 192. We want to convert 192 into binary. Here's how it works. Always start on the left side. So it'll start 128. We say, question is, can you fit 128 into 192? Another way of thinking about it is 192 bigger than 128? And the answer, as we know, is yes, you can. Now, we don't write down yes, we write down 1 because you can store it. Now, because you've kind of poured 128 into there, you take 192, take away 128, leaving you with 64. And now, because we've only left with 64, we can say, does 64 here fit into 64? Well, it does, and conveniently it fits perfectly. And now, because we've accounted for that 64, we take 64 off this, leaving us with 0. And now, as you can imagine, or as you can see, for the rest of all of these, the results will be 0, because you can fit 32 goes into 0 times, 16 does 0, and 0, and 0, and 0, and 0, because 192 was accommodated with 128 and 64.